deal with arc length in parametric. You've already done arc length for rectangular. Let's make sure that you remember the formula. So, right, rectangular is when we're given y as a function of x. We move rectilinearly left, right, up, down. We've already done arc length. I had it on your last test as one multiple choice question to keep it alive. We'll derive our new one for parametric motion from it. So see if you remember arc length formula from our chapter, I think it was our chapter 1. It was one of the first new things we did, is an arc length. So just see if you have that down. You might be wondering, well, how will I know which formula to use? It depends on the movement. If it says y equals 4x squared minus sine x, that's rectilinear. If it says y equals cosine t plus t squared, that's parametric. So you might have to be a little intuitive on which formula to use. But arc length, here we go. What did you write first? It's an integral from a to b, then what? Square root 1 plus what? Yeah, thank you for not saying f prime. The dy dx part of it is important that it's in that, what we call Leibniz notation, so that's good. There's my arc length formula. We used it, we derived it, it was easy. I don't think you've forgotten it because nobody got it wrong on the last test, not one person. So that's alive and well and cooking, and now we're going to have a new one, the parametric version. So for the parametric version, what I need to do is have it controlled by t. My integral is going to have to be limits of t. My differentiable is going to have to be dt. And I'm going to basically have to get rid of all the dx stuff in there, really. So it'll go parametric. What I am going to do first is yesterday's formula for how we do a parametric slope of the tangent line. I'll replace this. So all I'm doing right now is a derivation. You'll never be asked to do one, but they really help with your higher level kind of thinking skills, I guess. I'll replace the dy dx with dy dt, right? Over dx dt from yesterday. That's going to get squared dx. So far, not good. This is not dt, right? But I will get it there. Here I go. So the next thing I'll do is what we always do when we're adding fractions and we want to clean it up. We do our cross products or crisscross and then multiply across. So I'm going to take this sum and we'll make it one single fraction. So I will do dx dt quantity squared. So I'm doing my crisscross go across. Dx dt quantity squared. And then I have my plus dy dt quantity squared. All over, and it's still all under the root. And I'll have on my bottom there dx dt quantity squared. I'm going to stop for a second because I wrote that fast and let you catch up. But are you all right with what I did? Yeah, all I did was take dy dx, replace it with its parametric form, and then I just cleaned up my fraction in there. Now I'll just use some basic radical rules that when you have the root of a quotient, you can do them separately. So the bottom is going to kind of disengage itself from under the root here. I'll have a dx dt still, because I can't deal with that sum, but here's what's going to happen on the bottom. I'll take the root, and I just get dx dt. So the only thing that's really my issue in here that's not being controlled by t is this differential over here. Do you see how it's now going to become dt? Because what am I going to do instead of dividing by dx dt? I'll multiply by a reciprocal, and it'll get rid of that dx differential. So basically, I'll take this guy, I'll flip it over, dt dx, and now I have a workable model when I'm given my parametrics. I can find the derivative of x with respect to t. I can find the derivative of y with respect to t. It's now dt. Guess what my limits are now in terms of? They're no longer limits for x. What are they limits for? T. Yeah, so if they say t element of 0 to 2 pi, I go from 0 to 2 pi, because now this is all about t. So what I want you to do is take a look at this. This needs to be memorized. It's going to tie into another formula that we have. Not yet, but I'm going to have you write it ahead of its time, so when we get there, maybe you'll have a little aha moment. Arc length is really total distance traveled. If we're talking about particle motion, and I say a particle is traveling along that path, if I were to ask you what's its total distance traveled from this dot to this dot, that's really code language for what's the arc length. Agreed? This is really going to correspond to a formula we get for total distance traveled. Let's go to the rectilinear formula though and see what goes on. When you find total distance traveled prior to today, when you weren't moving all over the place, just along the x-axis, what did you integrate? Do you remember for total distance traveled, what did you integrate? Absolute value of velocity. What's another name for the absolute value of the velocity? Speed. For parametric motion, this expression right here is actually going to be the speed of the particle. Absolute value is not there, but what happens when you square anything? It's positive, so that shouldn't cause you an issue. That eventually, someday next week, we will have a formula for speed, and it should not surprise you at that time that this is going to be our formula. It's actually going to be what we call the magnitude of the velocity vector, but for now, we'll just say technically you're still going to be integrating the speed to find total distance traveled. But today we're calling this arc length, and you are not connecting it to speed at all. But I told you there's lots of formulas. They all look similar. So if you can have something to keep them straight, that's great. All right. So now I'm going to veer again. I'm just going to show you where this is used historically because it's interesting. I have a little typo here. It should be 2 pi r. So way back in, 5th grade, when you did circumference of a circle, Megan was told that to do the circumference of a circle, she does 2 times pi times r, right? Why? There's an easy explanation that's not as formal, and a formal one that we're going to do. You could say it goes all the way back to discovering pi as a naturally occurring constant, right? Maybe sometime historically they realized that no matter when they divided the circumference by the diameter of any circle, they always got pi, which would mean c is pi d, right? So 2 pi r is c. But you can prove it with an arc length formula because a circle really is an arc, and the path that it travels from here to here, its length is the circumference, right? I'll do it 2 ways. Rectangular, which is long and ugly, parametrically, which is nice and short and easy. And I have these solutions light, so you can. I want to work it out. So here you go. Are you ready? Say yes. Yes, Miss LaRude. All right, here we go. We're going to do the arc length in a rectangular format. So for that, I would need to integrate. All right. I'm going to go from 0 to r. So like, I'll do 4 of them though. I'm just going to do this piece of it. I do the square root of 1 plus dy dx quantity squared. And again, if you don't understand what I say in the next, I would say about 8 minutes it's going to take me to do both of these. That's okay, not on Smile. Don't have me stop because you won't ever have to derive these. But for the half of you who can understand it, it's kind of cool, and it gives you some historical significance for this. So if I was doing this prior to parametrics, I would use this guy because this guy's the rectangular form for standard form of a circle. This one's been parameterized, correct? Billy, it shouldn't surprise you if I had you eliminate the parameter on this one, you should get that, right? Do you see the connection? They're both circles. What does the parameterized one have that the rectangular one doesn't? Control over it. Yeah, orientation, speed, direction, all that good stuff. But I'm going to deal with this guy right now and pretend I didn't learn parametrics yet, and I'll come up with the circumference of the circle. It requires me to find the derivative of y with respect to x. How would I do that in that scenario the slickest way? How would I find dy dx for x squared plus y squared equals r squared? Implicit would be the easiest. Or maybe we remember the slope fields where I said I looked at the Diffie-Q and I go, oh, I know that one's a circle because circle's always something. Do you guys remember what it was? There was one. It almost negative x over y, but it doesn't matter that you don't remember it because just Sophie saying implicit gets us there super fast. Keep in mind, r is the radius of a circle. It's a constant. Its derivative is 0. So if I were to do a little implicit on here, the 2's I can divide out. I'll subtract x divide by y. I know I'm going kind of fast. 2 reasons. I'm on a time crunch, and you don't need to know how to do this. It's just kind of cool. So Lindsay, I have my dy dx be negative x over y, correct? So I'll go back to this. 1 plus x squared over y squared dx. You should know by now, having been in calculus of a single variable for a year and a half, who the issue is up there. Who shouldn't I probably have? The y. Yeah, I can't mix those. It's a differential of x, so I really need my limits in terms of x. And you might say there in terms of r. The radius is what I'm changing, so that's why that's on the top limit there. But over here, I need to clean this up. I'll do what I did on the last one. When you're have the task of cleaning up a sum of fractions, it's always to your benefit to crisscross and write it as a single fraction. Now I'm going to pause, because this move here is what gets you. You might say you just created y in more places. I did, but look at the top. The bottom is really, I'm going to have to write smaller. The bottom's really a y. What's the top? Square root of r squared. So what's really the top? R, which in this scenario is a constant, and it can come out front. Are you okay with that? So under here is really an r squared, and when I take its root, I get an r, but I'll pull it out front here, which leaves this. I still have a problem, right? But it's a simpler problem, but now I'm stuck unless I decide to do what? What do you think I'm going to have to do here? I have an option. What do you think? I can't have that y there. What did you say? What? I can't, because I'm only rectangular right now. I'm not dealing with the r sine theta, r cosine theta until the next problem. I'm still pretending I don't even know parametrics. I have an issue. The issue's y. It can't be there. There it is. Yes, thank you. I can count on you a lot of times for those types of questions, so I like it. You have value. All right, here we go. Yeah, I value you. Repeat what you said. What I'm saying is sometimes you drive me crazy, but you always redeem it, because that, just there, you just earned yourself a week of crazy. All right, so if you didn't hear him, he said, I don't know that he actually said solve for y in terms of x. He said the square root of r squared minus x squared, right? Do you see where he got that from and why? I don't like the y, but in my formula, I can always, that's the kind of, with function mode, you can always solve for x in terms of y, y in terms of x. Here's where we might get stuck, and here's why this is a Calc 2 derivation, and I didn't do it last year. I gave you an arc length formula that you didn't have last year, but also this integration. Don't blurt it. Somehow I have to figure out an integration technique that deals with this. And my first one that pops into my mind is u sub. And you're good. Thank you for not blurting, because she sees it. U sub's out. If only there had been an x on the top, I'd love it, because I'd have a u sub going. And then I think other things like maybe by parts, totally out. And then I think of partial fraction decomp. And then maybe I see that form that it's in, and it triggers some method. What is it? This is arcsine. Yeah, arcsine of a squared minus u squared, really. This is 4r from my constant and all that good stuff. And it's arcsine. Now you have to remember, so arctan, people remember, because I say 1 over analysis, arctan urine analysis. Do you remember what the sine one was? It's actually simpler, but arcsine urine analysis. Yeah, it's just u over a. In this scenario, who's u? X. Who's a? R. What if you don't get this? I don't care. You just nod and smile. You just go, yeah, I get it. But if you do, that's great. I'm doing it for the half of you who maybe get it, and I don't know who you are, and so I'm just going to assume you all do, because you're all nodding and smiling. It's running into my workspace, but I don't care, because the parametric one's going to be slick, which is why sometimes you parameterize stuff. When you plug the r in, you'll get arcsine 1. And then when you plug the 0 in, you get arcsine 0. All right. days like today are the days where I sometimes get the people who don't pay attention, because it's challenging, and that's kind of sometimes what you guys need. All right, so arc sine of 1 is equivalent to saying the sine of what angle is 1? What's this? Pi halves. The sine of what angle is 0? 0. Now what happens when you multiply 4r by pi halves? 2 pi r, the arc length of a circle or the circumference of a circle. Slick, right, Megs? All right. Now, if I did it parametrically, it's actually a lot smoother. So we are going to parameterize. It's already been done for us. But if we eliminated the parameter, we'd go right back to there. They are equivalent. All I'm doing is now controlling it. The circle that's rectangular is just, I could plop it down there, right? This one I can't. I start at a specific spot. I go in a specific direction. It's controlled by the angle. It's good stuff. But my formula now changes as well. This is parametric arc length, and this is what you need to know how to do today. There's two things at the level of your worksheet. This is one of them. This would be, I'm going to integrate from where to where now? Where am I going to integrate from? 0 to 2 pi, because this is controlled by the parameter, right? Next step, it's the square root. Do you remember what goes under there? It's not 1 plus. I just derived it. Yeah, it's dx dt squared. Let's go do that really quickly. What's dx dt? Negative r sine. I'm not going to write it. But then when I square it, I'll have r squared sine squared theta. You might say, that's way uglier. Oh, it gets so nice. When I do my dy d theta, because it's not dt isn't my parameter, theta is. So in your model, t's are thetas, thetas are t's. All right, so when you do the what am I on here? Dx d theta? No, dy d theta would be r squared cosine squared theta. So I need you to stare at that. That's going to come out really nice if you know what to do next. Don't blurt it. There's a really easy move that the whole root will pop off and you end up with such a simple thing to integrate. Pull out an r squared, and then you have sine squared plus cosine squared, which is, so you're really just square rooting r squared, which is really just, oh, that was painless, right? So a lot of times that happens with this parametric stuff is that's sometimes the whole point of when they do things in parametric or in polar is it's so much simpler that way. So this is just integrating. By the way, I'm going to choose, just for fun, because I'm going to do it in the next one, I'm going to go from my circle 0 to pi over 2, and I'll do 4 of them. Just because I'm going to have to, the next one I do has a cusp, and so I'm going, the circle doesn't, so I'd be safe, but let's go like that. I would have r d theta. Now be careful. Somebody last hour said r squared over 2. This is equivalent to a constant dx, like 3dx. What's its antiderivative? 3x. What's this guy's antiderivative? R theta. Yeah, so be careful when you're doing derivations and problems that aren't specific that you know what your variables are. Theta is an angle. D theta is me changing the angle at increments. R is whatever the radius of the circle is, which is a constant. 4 is a constant. This is just for R theta from 0 to pi over 2. Now when you plug it in, what do you get? 2 pi r minus 0. Agreed? So both ways. Who's simpler, rectangular or arc length? In this scenario, arc length. So now I'm going to move on. Now your worksheet, don't take it lightly because arc length can get messy. There's a couple things though. Because you're integrating and you're under a root and you're not going to math 9, that means at some point somewhere what's under the root's going to clean itself up like that one just did, right? If yours isn't, you're doing it wrong. This is also at the level of your worksheet. A little higher level than the AP will be just because of the manipulation. They tend to, like I said, test concepts more than the messiness. The next two I do get a little messy. So we're going to start. Make sure we know our formula. I know I'll use parametric arc length even though it didn't tell me because I can see the time parameter in there, right? It's not saying y is cosine cubed x. It's two functions, both controlled by t, which tells me I'm going to integrate square root of, and I'm going to write it one more time. What is it? Dx dt, quantity squared, plus dy dt quantity squared with respect to tiny changes in t. So let's go over here. I'm going to go over to some workspace. Let's do dx dt first. 3 cosine squared t times what? Times what? Negative sine t. Are we good with that? Just took a derivative of x with respect to t. Dittos on dy dt, maybe? 3. 3. Did I do something wrong? I'm taking the derivative with respect to t. I brought it out front, dropped it 1, took the derivative of the guts. Now I'm doing dy dt. I'm bringing that out front, dropping it 1, derivative of the guts. I'm good, right? Right? Are we not? But stop me if I make a mistake because there's a lot of detail. This one's not so bad. The next one, though, definitely keep your eyes open. So I will square them, and I shall hug him and pet him and call him George. Do you know what that's from? Foghorn Leghorn cartoon? No. So I shall square him and root him? No. Okay, here we go. All right, forget it. Google Foghorn Leghorn. There'll be a chicken. He has a little pet, something, I don't know. Here we go. 9. What am I in the process of doing? You guys don't throw me off here. I threw myself off. You're like, what do we do? She's blaming us. All right, there we go. There, I just squared dx dt. The negative went in the squaring. It seems like it's so messy. And I'm going to repeat something I said 2 minutes ago. I said you are going to be integrating. You're going to be integrating under a root. You're going to be doing it by hand, not on a calculator. So what's under the root will clean. If not, you did it wrong. Somebody tell me how this is going to clean and what you're seeing. Factor what? 9 cosine squared, sine squared, a nice perfect square. And what's going to be left? What'd you say? 1. So let's do that, disguised as cosine squared plus sine squared. But I'm going to show all the work for the people who are absent and who have to watch the video and can't hear what you're saying. What they said was factor. In particular, Addie Holland said it. Factor what? 9 cosine squared t, sine squared t. And then somebody next to her said times 1. Why? Because when you factor that out, you get cosine squared. I hate t's and pluses. Sine squared t dt. That's really what's under the root, which they create them. If you have to do it without math 9ing it, things are nice, things are pretty, life is good, except on the next one I do. Okay, this is 1. What's the square root of 9 cosine squared sine squared? What is it? 3. Yay. Now it's once you pop that root off and you're integrating, it'll be a technique you know. I'm not going to promise it's the same technique all the time. This one's nice though, right? What's its technique right now? What technique for this? U sub, who you? The answer would be either or, the better choice is sign. Why? Avoid negatives. We don't like them. We make mistakes. So we'd launch into some U sub. We'd be a little bit careful. This right here, I'm purposely doing something right here. Watch what's going to happen. Okay. On here, if I'm going to pull the 3 out front. I'm going to have you leave those limits off for a second. Because, well, let's put them on there. If you did U du, and you now go change your limits, and I tell you, this will be a trigger for you guys. If you go change your limits, because who is u in this scenario? We said sine t, right? Sine of 0 is 0, cosine 0 is 0. Technically, what am I integrating? From 0 to 0. What's the answer? 0. But that's not the arc length. I did something along the way that I didn't watch out for, and I told you guys to watch out for it earlier. Way back when I found my derivatives, right? I said be on the cusp alert because you can't mathematically integrate past a cusp. What I ended up with is nothing to integrate, right? We'll tweak it, and we're not going to have to go, if you're like, oh my God, we have to go do it all over again. No, not at all, but we do need it. That's what, if something weird, like I purposely did that. If something weird like that happens where you're like, what? I'm integrating nothing. There's no arc length. Well, yeah, there is. There's a path that's traveled. There is a number right away when you go from 0 to 2 pi. There's an angle that causes both of those to be 0. Who is it? Pi halves. Now I want you to take out your graphing calculator so you can see the path of this, so you can graphically see it. So just quickly, that's why I had to teach you the pre-calc of it. Are we going to use the graphing calculator like to throw balls anymore? No. Are you going to be parameterizing and all that kind of stuff? No. Can you do this on your calculator? No. But I want you to see what it looks like, and I don't want to have to stop and teach you how to enter it. So you should know to set your t from 0 to 2 pi. You should know a t-step of 0.05 or 0.01, probably 0.05, because we just want to see the picture of it is good. You should know that you should set your x's from -1 to 1, because these are cosine and sine. Set your y's -1 to 1. Ditto, and we should smoothly be able to see the graph of this. And I think this one is, make sure you're in radian mode, and you shouldn't be entering the derivatives. We're graphing the original functions, Ms. Heinen. I want to know what the original curve looks like and what I'm being asked to find. It is a hypocycloid. How do I know that? Because I just saw her graph and it's on yesterday's worksheet, right? It said graph the hypocycloid. It goes like this and like this and like this and like this. My goal is to find its arc length. I just said there isn't any. But that's because not only did I hop one cusp, how many did I hop? Yes, and if a function's not differentiable, it's not anti-differentiable, so it causes issues. Your calculator might hop the cusps. That I don't know, but you mathematically it had a problem. So tell me where in this, where can I immediately correct it? 4 times 0 to pi halves. That's why I did it on the circle one, just to keep you aware of it. So if we just go 4 times and then change this to pi over 2, and then let's just pretend it filtered all the way down so Mrs. LaRue doesn't have to rewrite them. This is really 4 times, and we're going to go for pi over 2. So I told you it wouldn't take long to fix. So the actual answer to this, u squared over 2, I have a 12 out front, and I'm going from 0 to, change the limits, right? 0 to what sine pi over 2? 1. Now, I will tell you, I have a linkage error. Find it. I'm kind of trying to keep you on your toes here and keep myself on my toes. I didn't make it on purpose, but I made it, so I'm going to call myself out on it. I have a linkage error somewhere. Do you see it? It's right here. Because what if I went to u and du, these are, what should these be? 0 to 1. Will you get docked for that on the AP exam? I have no clue. I don't. I know I was told for the one I was reading last year to do a linkage error for one part of it, but I doubt it. Actually, I'm going to tell you, you wouldn't be doing one like this. So, but the answer is 6. Your calculator had somebody first hour, second hour do this one from the get-go on their calculator and Math 9 it, and they got 6, which was kind of weird that your calculator was just fine cruising along those cusps. I'm wondering why, but I don't want to delve into it. I would think it would error out, but it doesn't. Next one, this is the one I really wanted to get to, and this is going on the blank sheet of paper. This is elk time, Thursday, 15 slots. I'm going to make 2 classes of 15, one for Calc 2 to do this, and one for Calc 1 to kind of be first come, first serve. So once that you're able to pop into that, I think they open it for you guys Friday at 2-ish, I think. Anyway, I'm going to do 15 for you, and then I have to reserve 15 slots for AB to do a, oh, are you kidding me? This just beeped in my ear that my battery died, and this is the exact one I was rushing to get to record. Okay, if it keeps beeping. See?